All right, let's talk about enthalpy and Hess's law. Now, enthalpy and Hess's law are going to be a little bit of review from last week in specific heats, and it's also going to introduce something new. So a little bit of math here, but nothing you guys can't handle. So let's jump right in. So what's the calorimetry connection to enthalpy and Hess's law? Well, calorimetry is going to measure heat flow into or out of a system. Right? That's what calorimetry does. A lot of the chemical reactions that we do or the physical changes that we study in the chem lab happen under constant pressure, right? And that lets us look at enthalpy. Okay, enthalpy is H, and we've discussed it a little bit before, right? But that is the variable H. Okay, if you have change in enthalpy, we obviously say delta H, and a lot of times we use the word heat and enthalpy interchangeably. And obviously, we would like to explain why. So, the measure of enthalpy change for a reaction, if you do it in aqueous conditions, right, um, involves two things. It involves the system and involves the surroundings. The system is the actual reaction that is taking place, the reactants reacting with each other. The surroundings are the water. Now, when we look at the thermometer here, we can see that we are measuring a change in the surroundings. So once the reaction is complete, we look at the change in temperature of the system, and that lets us calculate the heat absorbed or released from the surroundings. So if the temperature of the water goes up, then there must have been energy that was released by the reactants. It was absorbed by the surroundings. If the temperature of the water goes down, well, then the reactants absorbed energy from the surroundings, and that's why the temperature of the water went down. We can use Q equals MC delta T, which is the calorimetry equation for specific heat that we talked about last week, and that will tell us the heat of the surroundings. Now, it is important to note that that is the heat of the surroundings, not necessarily the heat of the reaction. Okay, so that little sub SURR means surroundings. Now, the heat that is absorbed by the surroundings is going to be equal to the heat of the system. However, they're going to have an opposite sign. So if I want to calculate enthalpy, I can say the heat of the system equals the delta H equals the negative heat of the surroundings. And that means we want to put a negative sign right there. Okay. So that's how we're relating these two things. If you get a positive delta H, then you're talking about an endothermic reaction. If you get a negative delta H, you have an exothermic reaction. Okay, so let's do a practice problem here. Let's see if we can analyze one of these. So the problem says the initial temperature of the water in a constant pressure calorimeter is 24 C. A reaction takes place and the temperature rises to 87 C. So we have 24 to 87. The calorimeter contains 367 grams of water, and we know the specific heat of water is 4.18 joules per gram Celsius. Calculate the enthalpy change during this reaction. All right, well, we know we're going to use the delta H formula we just talked about. So delta H equals negative MC delta T. So we're going to plug those variables in from the question. So negative 367 grams, 4.18 joules per gram Celsius. And then remember that delta is always final minus initial. So I have the final temperature and I have the initial temperature right there. So that is going to give me negative 97 kilojoules. So there we go. It's a negative, so this is exothermic. All right, and that makes sense. The energy given off by the reaction was absorbed by the water. The temperature of the water went up. So the energy given off by the reaction tells us that's an exothermic reaction. So let's look at something new. Let's look at this thermochemical equation. Now, up until this point in the year, we've seen equations that never had anything like this in it. This is what makes it a thermochemical equation. It's just added the energy, okay? So if I add it as a product, all right, then I'm talking about an exothermic reaction. That's something worth knowing. Obviously, then if it's on the reactant side, then we would say that it's probably an endothermic reaction. Now, when we talk about heats of reaction, right, that is the enthalpy change for an equation as it is written. We always report those in delta H, and we really have to make sure that the physical states of the reactant, so like gas or liquid or solid, is written. The standard conditions for our heats of reaction is 1 atmosphere and 25 degrees Celsius, so STP from gas law. When we look at heats of reaction, this is how we kind of break down this information. So this is a little different from a thermochemical equation because there is no plus sign here. It's just written off to the right, and there's a little equal sign there. So that's how you can tell those two apart. When I look at this, this tells me that each mole of calcium oxide and water that reacts is going to produce 65.2 kilojoules of heat. I know that because it's already balanced to have a 1-to-1 ratio all the way through. So each mole that reacts on the left, right, 1 and 1, is going to make that much heat. I know it's exothermic because I have a negative sign. All right. Here's the second one. Baking soda decomposes when it's heated. This process is endothermic. All right, how do I know that? Well, I have a positive sign right here. Okay, so this is a decomposition reaction, right? One reactant is breaking down into multiple products. So as it decomposes, it is absorbing heat. Okay, it takes heat to get that to happen. So why do we care about the phases? All right, well, look at these two equations here. We have water as a liquid, okay, and then we have water as a gas. These are two different delta H values, all right? So it's going to take an extra 44 kilojoules of heat to vaporize liquid water, all right, than it would to do the same thing there to water vapor, okay? So that's what we're looking at. Now, just so you're aware, you don't have to like know these numbers off the top of your head. There are tables, all right, that have all of these delta H values. There's even one in the back of your book. So let's look at this question. It says, calculate the amount of heat required to decompose 2.24 moles of NaHCO3. Well, here is our equation. Let's break it down and say what we know. We know how much of our sodium bicarb that's decomposing, 2.24 moles. That's from the problem. We know the delta H for the reaction is going to be 85 kilojoules per 2 moles of sodium bicarb. So what is the thing that we're looking for, right? We're looking for the delta H in kilojoules, because that's what the question asks for 2.24 moles of sodium bicarb. So how do we solve this? How do we answer this question? Well, same thing we do pretty much everything. We're going to use the factor label method. So here's our equation. We know that 2.24 moles of sodium bicarb. For every 2 moles, we use up 85 kilojoules, right? There is the conversion. 95 kilojoules is my answer. There we go. All right. Pretty simple, straightforward math. One bracket conversion there, just like we've done many times before. Now, heats of combustion is also something we talked about last week. And the molar heat of the combustion is the heat of reaction for burning 1 mole of a substance. So if we look at this reaction here, we know we have an exothermic reaction because we have kilojoules on the product side. All right. We know that we can calculate how much energy, is given off when you burn 1 mole of methane. Now in this equation, we have a 1 right here, so we can just relate these two things as a molar heat, which is pretty useful. All right, but if this was something else, all right, if this was say a 2 or a 3, right, we would have to convert. We would divide in that case. So when I remember that when we have this energy value on the right side, that it's exothermic. When we're talking about exothermic in terms of delta H, remember we have to make that a negative value. Now, we also have things called standard heats, and standard heats are the heats that are determined at 1 atmosphere and 25 Celsius. Anytime you see standard something, we're talking about STP, all right, 1 atmosphere and 25 degrees Celsius, all right? There are a bunch of tables, all right, that have all of these different standard heats of combustion at 25C. Notice that they include, all right, a phase. So like carbon as a solid in the form of graphite, which will be different than diamond, all right, is negative 394 kilojoules per mole. Methane as a gas, right? Let's see, do they have one that's no, they don't. All right, but in a given table, you may have like carbon C solid graphite, and then underneath of it, carbon C solid diamond, so on and so forth. So that brings us to Hess's law. And Hess's law is really useful in chemistry. And if you do end up taking AP chemistry with me, we'll spend a lot of time with Hess's law. Hess's law says this: if a reaction is carried out in a series of steps, then the delta H for the overall reaction will be equal to the sum of the enthalpy changes for each step. Okay, why? Why is this important? Why are we going to spend time on this? Well, it would really suck if you had to do an actual calorimetry experiment for every single reaction. But the thing is, we've already done a lot of calorimetry steps, or calorimetry experiments, sorry. And we've tabulated them. We've put all those values into a table. So if I know the series of steps that a reaction undergoes, and I have a table full of enthalpy values, well, then I know if I just sum the steps in the reaction, I can get the overall delta H for a new reaction that I haven't done the experiment yet for. And that's pretty handy, right? So here's Hess's law. Let's look at it in a graph. Here is the overall reaction. CH4 plus 2O2 is combusting to form CO2 and 2H2O. So there's the overall reaction. And overall, it's negative 890 kilojoules is delta H. We can look at this, though, as a stepwise reaction. So there is a step where the CH4 and the O2 becomes CO and 2H2O and a half an O2. Well, this is tabulated at negative 607 kilojoules. The conversion of this intermediate step here down to the bottom is also tabulated. And so I don't actually need to do the overall reaction. I just need to take these two values and add them together, and I'll get that value. That's what Hess's law says. If you know the steps, then you can add them together to get the whole. That's it. Now, enthalpy is a state function, and we'll talk more about state functions next week as we get into thermodynamics a little further. But a state function only depends on the initial state of the reaction and the final states of the products. It doesn't matter how you get there in between. So that's another reason that this works. And we'll talk more about state functions in the future. A lot of times, and we call these elementary steps, right? So when we talked about reaction rates and we talked about the elementary steps, this is just the elementary steps with some math. It's the exact same thing. So let's actually do one of these. Calculate the delta H for the combustion of carbon to form CO2. So this is what we're looking at. Now, in a table, I can find the delta H for this reaction from carbon to carbon monoxide is negative 110.5. And carbon monoxide plus oxygen is going to give me CO2. I can find both of those in the table. So I look at my reaction. When I add, this is where I want to get to, right? This is the final thing. This is what the question asked me about. This is what I could find in the table. So when I put those two things together, the CO cancels out. It's an intermediate. It's on both sides of the reaction. It's just like a spectator ion when we did net ionic equations. If it exists on the left and it exists on the right, when we add two reactions together, then we cancel it out. We also add our enthalpies together because that's what Hess's law tells us to do. And so without burning any carbon, I can tell you that the combustion of carbon has an enthalpy of negative 393.5 kilojoules. It's just adding, all right? Now these tables, where are these tables? There are lots of these tables. Check page 971 in your book, okay? That's where a lot of our enthalpies are tabulated up. And there are enthalpies for vaporization, fusion, combustion, formation, all these different things, okay? So depending on what the question asks you for, that's the table value that you need to look up. All right, remember that if you see a degree symbol on delta H, so if you saw like delta H prime, is how we say that, then that tells you, that signifies that the reactants and the products are in their standard states, okay? That is the state that that thing exists at under standard conditions. So we know that STP is our 25C and 1 atmosphere of pressure. So when we look at standard state and we say, all right, well, what would oxygen be at standard state? Well, it would be a gas because at 1 atmospheric pressure at 25C, oxygen is a gas. That's what it is. So it's standard state, right? As in standard state of matter, it's gas. Carbon is going to be solid, right? The standard state of water would be a liquid. So when we look at these standard states, the tabulated values are for those specific phases. Now, sometimes you'll see enthalpy of formation, so delta H sub F prime. Again, this right here tells you standard state. The F tells you formation. All right, what is formation? What are we talking about? Well, that's when you make a compound from its constituent elements in their elemental forms. All right, what does that mean? Well, if I want to make CO2, I'm going to make it from its elements in their elemental forms. So O2 is normally a gas. Carbon is normally a solid, right? So these are the elemental forms to make this final product. So this would be, if I wanted to find that enthalpy, I'm finding the enthalpy of formation. This is what they look like. The table's in the back of your book, right? 975 has enthalpies of formation, and it gives it to you in kilojoules per mole. So when we do calculations with that, we need to find that in kilojoules per mole. Gives you the formula with a phase, right? Gas, liquid, whatever. And remember, those are the phases that thing exists. Here's another standard enthalpy of formation table. Now, notice on here, there are some zeros right there. So if you have the most stable form of an element, that is going to be zero. That's the enthalpy of that formation is going to be zero. There is no formation to occur because it already exists in that state. So like, I hope that makes sense. How can we think about that? Let's see. You can't form something that's already present. That's really what that zero is saying. So under standard conditions, bromine, right, already exists. So it doesn't take any energy to form it because it's already there. So if you see a zero, all right, that is the most stable form of the element. There's a bunch of those on there. They're useful, all right? And now we can finally put those two together. So when we put those two together, those two things, we come up with Hess's law in terms of math. So we have the delta H's of formation, and we know what the overall Hess's law is. And this is what it says. Delta H is equal to the sum of the enthalpies of the product multiplied by their coefficients minus the sum of the enthalpies of formations of the reactants multiplied by their coefficients. Not complicated. You take the enthalpies of the reactants, you subtract that from the enthalpies of the products, and that gives you the total delta H of the equation. That's how they find those values. So let's look at one of these. We want to find the delta H for the following reaction. We have C3H8, so that's propane, and 5 oxygens, and we're going to make 3 carbon dioxides and 4 waters. So this is the equation that we need. And so we go to that table. And here is our table. So let's break down this math. So this is the enthalpy of formation of C3H8. All right. Oh, no, sorry, of CO2. Geez, products on the left. All right, there's CO2. And here is the enthalpy of formation of water. There's its coefficient. 4H2O, 3CO2. So those things are married. And we're going to subtract it, right, from 1 C3H8. 8. There we go. Oof. All right, and we're going to add that to 5. O2. Now look at O2. It's a 0. So like this number goes to 0. So I'm just going to do those things together, right? 3 times negative 393.5 plus 4 times negative 285.8. I'm going to subtract. Actually, I'm going to end up adding 103, right? Because negative. And there we go. That's it. So you have to use the table. This isn't hard math. It's just you got to use the table. If you don't use the table, you're sunk. All right. So use those tables. You can use the one in the notes. You can use the one in the back of the books. Okay. So let me know if you have any questions. All right. We're not going to go much like super in depth with this. We just want to know how to find enthalpies. We want to know some definitions as far as enthalpies of formation and all that stuff, okay? So let me know if you have any questions, and I'll see you guys in the next video.